So suppose that we were to write down the following expressions with exponents. 3 to the second is 9, 4 to the third is equal to 64, that's our answer, and also 2 to the fifth power equals 32. We can use a new function called a logarithm to rewrite these expressions. For example, if we took the first one, notice that the base is 3. So using this new function, we can say log base 3, and our answer was 9. So log base 3 of 9 is equal to the power, which is 2. So logs are powers. All logs are asking are what power are you going to raise the base to in order to get the argument, which is 9. So let's say that we were to try to rewrite the second one using logs. Our base is 4, so it's log base 4. Our argument would be the answer for our exponential expression, which in this case is 64. So log base 4 of 64 is equal to, and remember, logs are powers. So what power would we raise 4 to in order to get 64? That power is 3. So suppose we were to do that to the last expression here. So log base 2, the argument is 32, and the power is 5. So log base 2 of 32 is 5. In other words, 2 to the fifth power is 32. 2 to the fifth power is 32. 4 to the third power gives us 64. 3 to the second power gives us 9. We know that y equals ab to the x is going to look like one of two things. Of course, there are other transformations that can happen, but overall, we're either going to be presented with growth if the absolute value of our b is greater than 1, or we're going to be presented with decay if, again, this b value is between 0 and 1, or rather the absolute value of it is between 0 and 1. But what would happen, or what would the graph of our log function look like? So what exactly would this look like? Here we have log base b of x graphed. And here we're saying that b is equal to 1.3. But what if we increase the value of b? What exactly is happening to the graph? If we notice, the graph is actually getting flatter and flatter. But there's one thing that seems to be happening, that there's still a vertical asymptote where where x is 0. So notice as well that if we were to go the other direction, that our graph, so if we have our b values here that are between 0 and 1, that it's going the other direction. It's almost similar to what happened with our exponential functions. So are there certain things that we can say about our logarithmic functions? Certainly, in all the cases that we've seen, no matter which direction that we go, we don't have anything on the left side of the graph. Our x values always have to be greater than 0, or rather our base values have to be greater than 0. So b has to be greater than 0. So what exactly does the graph of y equals log base b of x look like? So far we can see that there are really two cases for this particular parent function. But in either case, we know that we're not going to cross the x equals 0 line. In other words, we're going to have a vertical asymptote at x equals 0. So when b is greater than 0, then our graph will look something like this. When b is between 0 and 1, our graph is going to look the other direction, something like that. We know that our logarithm function could be log base 2 of x. We can have log base 3 of x. We can have many different variations of this. But remember, e is a number. Remember, e represents a number that's approximately 2.7182, etc. It goes on forever and does not repeat, just like how pi does. So we technically could have something that looks like y equals log base e of a certain number. But that's entirely too much to write. So what mathematicians prefer to do is just to simplify it and call log base e the natural log or natural logarithm. So y equals ln of x is another way of writing that. So all this means is that we're doing a log and the base is e. What do we notice about the graphs of the log function and the exponential function 10 to the x? Basically, it looks like there's symmetry along the line y equals x. So they reflect along that line y equals x. So what that tells us is that the logarithmic function and the exponential function, that these are inverses of each other. Remember, inverse functions will always be symmetric with respect to the line y equals x. So what we can see then is that the log function and the exponential function, that they're inverses of each other. So if we compose them, that it should just leave us with x. In other words, if I have 10 to the x as a function, and I do log base 10 of x, and if I compose these two, it doesn't matter how I compose them. I can say 10 to the log 10 of x, it would just give me x. Or if I composed it the other way, where it's where it's log base 10 of 10 to the x, however I compose it, I'm just going to end up with x. This is true even if the base is something different. So if we do log base 2 of x and compared it with 2 to the x, if we compose these two functions, such as 2 to the log base 2 of x, or if we did log base 2 of 2 to the x, however we look at it, however we compose it, we're just going to end up with x. Again, this is true even if the base is e. So if we have the function e to the x, and we have the inverse of that function, which is the natural logarithm. So the inverse of this function, let's say, is ln of x. Remember that this just means log base e of x. And if we compose them, such as e to the ln of x, or if we did ln of e to the x, in either of these cases, we would just end up with x.